today, my goal here is to give you an idea of this beautiful correspondence between the on-shell diagrams we talked about in the case of planar theories with maximum supersymmetry, so where we get to ignore non-planarities, we'll talk about that tomorrow, but where we get to avoid or set aside the question about orienting these graphs, which is what you need to do, so you decorate them for n equals for non-supersymmetric, non-maximally supersymmetric theories. So this correspondence can be summarized here. So as a kind of an overview of the talk, we're going to be covering a lot of these arrows. So we have these on-shell diagrams in a planar theory with maximum supersymmetry. So two colored graphs where the edge of all of the external particles can be listed on a disk, and in particular we always orient or order them clockwise around the edge of the boundary of the disk. So what I'm going to show you is that these diagrams you don't actually need to draw. And in fact, planar n equals 4, which also includes all tree-level processes in pure Yang-Mills, can be entirely captured combinatorially. In fact, we can just throw away the graphs altogether. And in fact, this graph is uniquely characterized by this permutation or a decorated permutation among the external labels. We'll walk through that. But this permutation also labels a geometric configuration inside the Grassmannian of 4 planes in n dimensions. And this configuration is directly related to a way to encode the function. So this was the claimed correspondence on in the beginning of the first lecture, that there's a representation with a volume form, a very simple volume form in this way. Yeah, and so there's all of these have arrows between them, and we're going to talk about most of these arrows in this lecture today. So we have a lot of material to cover, but the theme is that the diagrams, the physics, are entirely combinatorial, and if you just knew the permutations, you could reconstruct the functions, you could understand the geometry and the relations among them and everything else. And this aspect of the story does not depend on maximum supersymmetry at all. It's true regardless. We'll talk about non-planar theories next time. Okay. So, recall from the first lecture and from earlier lectures that BCFW, at least diagrammatically, can be represented this way, and there's a grading according to m, the number of minus helicity particles. That's why we have the difference between the MHV and NMHV and squared MHV, etc. And in particular, this is from the previous lecture, we noticed from these recursions that first we could get these funny looking pictures which kind of scare us, and they satisfied relations that weren't especially obvious from the way that these diagrams are drawn. And for this reason, if for no other reason, this is probably why physicists stopped drawing these pictures, because it's just, why even draw this rotated thing when you know that it's actually equal to the rotation of this one? And so the fact that you can draw multiple diagrams that have exactly the same functional form, when you do all of the work, multiply all the vertices together, integrate over the on-shell phase space, and you get the same answer, this redundancy in these pictures is probably why they stopped being drawn by physicists. But which is a shame, because exactly at the same time that physicists stopped drawing these diagrams, Postnikov and his students and collaborators started drawing them for reasons completely unrelated to physics. And it would take us many years to cross paths and really learn the combinatorial foundation of all of this. So the basic, in fact, there are only two simple identities that you can do among these diagrams that leave the function on the outside invariant. And they're very simple to understand. The real identity is between this picture and this picture, and it's easy to understand that a tree of same colored vertices can be rearranged in any way you'd like, because the momentum conservation here just says all these lambdas, lambda tildes are proportional to each other, and same here, and you can easily see that it transmits the same way across this diagram. And so if you, depending on your taste, you might say that a tree of same colored vertices inside a diagram should just be collapsed and called a single vertex, in this case a quadrivalent vertex. And by that way, you can always talk about bipartite graphs where there are only edges between blue and white vertices. I'm not going to take that attitude in this talk, mostly because I like the 3-particle vertices. But the other one, and this is the much less trivial identity, is actually a consequence of BCFW. This fact that this little box of same colored vertices represents the 4-particle tree amplitude. And because of that, And this is also equal to the 4-particle tree amplitude. And the equivalence between these two amplitudes means that I can take a square anywhere in the graph and I can rewrite it this way. And that will, and so these are the two identities. And in fact, these turn out to be the only two identities that relate these on-shell diagrams, as functionally. And now it turns out that graphs that are related, or the equivalence class of diagrams that are related by these that are equivalences, are entirely characterized by a permutation defined in a very relatively simple way, which is you start on the outside of the graph, and as you enter the graph, so you start at leg 1, say, and as you enter the graph, every time you see a white vertex, you turn left. So that goes 1 to 2, 2 to 3, 3 to 1. And that gives you a permutation among the external labels. It's easy to see that it's a permutation, namely that everything has an image among the outside and nothing gets mapped to twice. In particular, you can reverse all the paths. So you know that every image has, every pre-image has an image and vice versa. So it's easy to see that this is a permutation. And it's easy to see, and similarly, when you see a blue vertex, you turn right. So 1 goes to 3 now, and 2 goes to 1, and 3 goes to 2. So it's easy to see that these moves, these equivalence moves, leave invariant these permutations. And it turns out that this is all of them. And the converse is in fact true for graphs that have the same number of faces. Namely, that if it turns out that if two graphs have the same permutation label, then they are related by sequences of moves. Although it's easy to see in very simple examples how long this can take, how many moves are required to get from one graph to the other. So recall, I mentioned this morning, and I just reminded you that there's an equivalence, that this diagram, this function here is basically the same as this function, just with rotated labels. So concretely, I'm claiming that this on-shell diagram with these labels is equal to this on-shell function is equal to this on-shell function. And we can do this by just checking their permutations. And in fact, this is sufficient because they have the same number of loops in the graphs. So it's a nice exercise. So 1 comes in here and it turns left at white, and then it turns right at blue and left at white, and it goes out at 3. And similarly here, 1 goes in, comes out at 3. So we'd write down 1 goes to 3. And then 2 goes to 5 in both cases. 3 goes to 6, 4 goes to 1, 5 goes to 2, and 6 goes to 4. And you can believe me that it's a theorem that if they have the same number of faces, if they're reduced, that's a technical word, then they are related by moves. And I'll leave it as a homework to construct the sequence of moves that connects this graph to that graph. But something that's visually not obvious at all, and it's actually a sequence of several moves, is entirely identified by just checking that they have the same permutation. Now, for various technical simplifications later on, it is useful not to say that 4 goes to 1, 5 goes to 2, and 6 goes to 4. Just by convention, this is purely a convention at this level, I'm going to require that the image of every permutation, every leg, is at least greater than or equal to itself. So, and when you see 4 goes to 1, instead of saying, because that goes to something less than itself, I'm just going to say that it goes to 7. Because 7 mod 6 is 1. So this mod n, the permutation label mod n, is just a normal permutation. These are called decorated permutations, in particular because there is an important subtlety that we don't care about right now, but we will later in the general toolbox, that there is a distinction between something that goes directly to itself and something that goes around n and to itself. So there's a distinction between, for fixed points of a permutation, there's a distinction between going directly and going to itself plus n. Okay, but for all the graphs that we're drawing here, this distinction is just irrelevant to us. It'll just be part of a cleaner toolbox later on. Okay, so the merge and square moves generate all the relations, but there's still an infinite number of graphs. There's one more important semi-identity, which is called reduction or bubble deletion, and it is not, strictly speaking, an identity. This follows from BCFW. You could imagine adding a BCFW bridge to this edge, and what you see is that it does not change the flow of momenta through the other edges at all, and so it's fairly easy to appreciate that whatever this on-shell function is equal to just a overall prefactor of d log of the amount of momentum flowing through there times this on-shell function. So this is not a true identity because it's not saying that this on-shell function is equal to that on-shell function. It's this on-shell function is a trivial prefactor times this on-shell function. And bubble deletion now changes the number of faces in the graph. With bubble deletion and these square moves, it's now easy to see that it's a theorem that the number of inequivalent diagrams or equivalence classes of diagrams is finite. Why? Because they're all labeled by permutations. The number of permutations is finite. It's a very large number, but it's finite. And yet there's an infinitude of graphs. And all that infinitude of graphs, when you combine bubble deletion with permutations, gives you a finite list there. And by the way, it does alter this left-right path thing. These prefactors are important for loop integration at some point later on. Okay, so I already mentioned one of the most useful tools for building up diagrams, or at least expanding your vocabulary. Once you have some on-shell functions, you can start building up a broader class of on-shell functions by adding a BCFW bridge. So if you take this, whatever this diagram is, and you attach a bridge, we know that it shifts the momenta flowing into this graph, and it adds a d alpha over alpha to it, et cetera. But it's interesting to know what happens to the permutation, because adding this this bridge has the effect of permuting or transposing the images of legs A and B. So that's all it does there. And that means that this graph is labeled by almost the same permutation as this graph, just with one transposition among the images of A and B. Now that's something that's kind of cute, but it turns out to be an extremely powerful observation when you read it from right to left. That if you had a permutation here, sigma prime, well, let me remove the prime, or move the primes over. Imagine you had this on-shell function. Well, it is related to a simpler one with fewer edges, labeled by a slightly different permutation by adding a bridge. And we know what adding a bridge does to the momenta. And so by this observation, if you recurse it, it tells you how to actually construct a function iteratively in terms of something simpler. And I'm going to show you how that works in glorious detail. There are many ways of decomposing a permutation into adjacent transpositions or adjacent-ish transpositions in terms of sequences of bridges. And one rule is one that will never fail you, but there's many other ways of decomposing these things, is the following rule. It's a very simple rule. So the rule is this. You look at a permutation, and you ignore anything that goes to itself, any leg which maps directly to itself or itself mod n, or plus n, you skip over those things. And then you look at adjacent pairs, and you look for the very first pair such that the images are ordered, so that 1 goes to 3 and 2 goes to 5. The images are ordered, and then you're going to write that permutation as a bridge on the transposed, on a diagram with the transposed permutation. So what does this mean? So suppose, this is related to the question of can you eliminate the graphs entirely? Instead of emailing you, if I wanted to send you a formula for an amplitude, or I wanted to refer to a specific function, until now, I would have to send you a big graph, and then you'd have to compute this thing in some annoying way. If I just gave you the permutation, just emailed you a lot of permutations, could you reconstruct the function directly, and can you construct a representative graph that has that permutation as its label? And the answer is this, and it's constructive. So you look at this, and so imagine I'm thinking of a function that's labeled by 3, 5, 6, 7, 8, 10. I can't remember if that's exactly the one that we just looked at or not, but it doesn't matter. So suppose you don't know anything. You don't even know what amplitude it's relative to or related to. All you know is that this is the permutation label. So you have no idea what's inside F naught here, what's inside this graph. Well, you do know for sure that whatever it is a BCFW bridge, d log alpha 1, times something simpler, F1, where it's labeled by this permutation. Okay, now you follow this algorithm till the end, until you get to the identity. So you, again, look at the pairs of columns, the adjacent pairs. Nothing goes to itself yet. 1 and 2 are no longer ordered, but 2 and 3 are ordered. So you write it as a BCFW bridge on that. And now 3 goes to itself, so we're going to skip over it from now on. But now 5 and 6 are ordered, so it's a bridge on something simpler. This algorithm will terminate at the identity. And there's lots of ways of decomposing a permutation into a sequence of adjacent transpositions. This is just one algorithm that's guaranteed to work. And at the end, you're going to eventually hit something that has every leg going to itself, okay? And you've now semi-constructed a formula for this function that you don't even know yet. It's a sequence of BCFW bridges on whatever is labeled by this identity permutation, which should be really easy, although it's certainly an on-shell diagram that I don't think anybody really looked at seriously until it showed up as part of this technology. So it's just a little too trivial. But what on-shell function is labeled by that thing? Well, this on-shell function is F0, the one that we care about. That is F1, that's F2, this is F3. You keep going, and when you get to F8, you get this kind of empty diagram. Now, what the heck is that as an on-shell function? It's a pretty simple on-shell function. It's got a ton of delta functions. It just says that all the momenta flowing in from the outside is 0. The coloring now, and the difference between things that go to themselves plus n, like 1 goes to 7, is a little different than 3 goes to 3. And it's reflected in the coloring that survives when you remove all of the edges. So you just delete all the edges, and you get these little hanging lollipop-like things. And it's preserved in the color of these vertices. And this distinction is telling you in spinner helicity whether it's the lambda that's vanishing or the lambda tilde that's vanishing. Okay, so what this is that it says that lambda tilde of particles 1, 2, and 4 are 0, and lambda of particles 3, 5, and 6 are 0. That is what this on-shell function is down here. And I claim that if you just do a sequence of BCFW shifts, 8 shifts, you get the function that we care about, the secret function that we don't know yet, or that we don't have a formula for. Okay, let's look at this a little bit. It's worth bearing in mind what this thing is. So first of all, notice that it composes 2 constraints per particle. It is either imposing that both components of lambda tilde are 0 or both components of lambda are 0. So there's always 2n delta functions. For 6 particles, there's always 12 delta functions. And obviously, as always, 4 of those 12 or 4 of those 2n just encode overall momentum conservation, which is, so there's a net 2n minus 4 constraints imposed on the momenta. Okay, now this function can be represented in a slightly more suggestive way as follows. Let me just introduce this 3×6 matrix C. Now, the statement that the lambda tildes of 1, 2, and 4 are 0 is very easy to say, but that it's C dot lambda tilde. Why? Because if you dot this into the matrix, if you sum over the particle number, then lambda tilde 1 equals 0, lambda tilde 2 equals 0, and lambda tilde 4 equals 0. So this set of delta functions is easily encoded here by this 3×2 matrix of delta functions. What about the other one, having the lambdas equal to 0? Well, this 3×6 matrix has a very natural orthogonal complement. Instead of the identity in columns 1, 2, and 4, it has the complementary identity, so in columns 3, 5, and 6. And that's what we'd call C perp. Well, so C perp dotted into the lambdas should be 0. That tells you that these particles have their lambdas vanishing. So we can therefore write this simple thing, whatever it is, that just imposes a ton of vanishing of momenta in a relatively simple way. Now, what is interesting is that when you add a BCFW bridge, it does not affect the delta functions at all. The delta functions just sit there for the ride, or at least a number of them. It doesn't add any further constraints or anything like that. So the fact that we have 12 delta functions, 4 of which are momentum conservation, is going to be preserved as you go. And if you work it out, and I'll leave it as something of an exercise, when you add a BCFW bridge between legs A and B, white to blue, what it does is it ends up shifting column B by some multiple, by this multiple, the bridge parameters multiple, times column A. So what it means is that going from this graph to F7, which is adding this BCFW bridge between legs 4 and 6, shifts column 6 by alpha 8 times what column 4 used to be. So if column 4 stays the same, it doesn't move, but column 6 gets alpha 8 times column 4. So that's what you get there. Otherwise, the formula is basically intact. And then we add alpha 7, and it shifts column 4 by column 2. And then we shift column 5 by column 4. We shift column 2 by column 1, etc. And what you end up building up is a matrix, a 3×6 matrix that depends on 8 bridge parameters, these 8 silly degrees of freedom that don't mean anything to us right now. But how many delta functions are there? There are 8 plus 4 for overall momentum conservation. There's 12 total delta functions, which means that you have exactly 8 extra delta functions and 8 unknown parameters. This thing, if you integrate it, locks all of the alphas to unique values, and that is the function. And they become functions of lambda and lambda tilde, and that is the function in question. So this is this we can think of as a subspace inside the matrix, inside the space of 3x6 matrices. It's an 8-dimensional space in terms of these coordinates, if we'd like to view them that way. Okay. In fact, it's worth noting that this is not necessarily a generic, it's not a generic 3x6 matrix. Why? Because notice that this minor is 0. Columns 1, 2, and 3 are proportional. They span a 2-dimensional space, as evidenced by the fact that the bottom row of this minor is 0. So this has one condition on it relative to a generic 3x6 matrix, namely that minor 1, 2, 3, that 3x3 determinant is 0. And we can actually bring it up to what we would call the label for the top form, which is very simple, by shifting back one more level up relative to our f naught. So we call like f minus 1 or something. And we shift column 1 by column 6. We do that, and now we have a generic 3x6 matrix. No minors are 0. It's good that there's 9 parameters because the space of 3x6 matrices modulo GL3 is 9-dimensional. So this is a generic configuration inside the Grassmannian. So it's a generic, this parameterizes the full Grassmannian. Now, I haven't actually mentioned anything about positivity, or at least from this point of view, it's going to be an accidental feature. But I will tell you that if you compute the ordered minors of this matrix, so minor 1, 2, 3, 2, 3, 4, 1, 3, 5, etc., all ordered minors of this matrix are positive sums of monomials of the products of the alphas. What I mean is that if the alphas happen to be real positive numbers, whatever they are, then every single minor of this matrix is positive. That's interesting geometrically because a 3x3 minor computes the area of a triangle in P2. So if we think about the columns as representing points in P2, which is kind of the same configuration space that we're talking about for the Grassmannian, then it means that for generic positive real values of alpha, they don't need to be real. There's nothing in this story that needs to be real. But if you just imagine that they're real, this actually describes a convex polytope. Because triangle 1, 2, 3 is the same orientation as 1, 2, 4, has the same orientation as 1, 2, 5. It doesn't twist on itself at all. So it's actually a positive, it is a polytope, a polygon, in a convex polygon on the plane. This is just an accident right now, as far as we're concerned. And you can see what happens when you send alpha 0, say, to 0. What happens is minor 1, 2, 3 is equal to 0. Now, what happens if we keep going down? Like, what happens if we send alpha 2 or alpha 1 to 0? When we send alpha 1 to 0, it sets a few other minors to 0. And what happens is the columns 2 and 3 become proportional to each other. You can see that they are proportional up to this is alpha 2 times column 2. So they're projectively the same point on the plane. And we can keep going like this. And we can go walk down the sequence and delete all of the, set all the variables to 0, and we recover this final configuration, which is the one that we started with, where it's just columns 1, 2, and 4 are non-vanishing. So there's some interesting, curious configuration. The sequence of simpler configurations follows this criteria that there are always positive polytopes. And thinking about how to organize what are the space of not necessarily generic polygons. So when I say not necessarily generic, you are allowing things like this to happen, where 1, 2, 3 happen to vanish. So it's no longer a generic hexagon, but you're allowing that. None of the minors are negative. So this is the totally positive or the totally non-negative Grassmannian, it turns out, is characterized by the same kind of stuff. But that's kind of an accident from our point of view right now. Okay. So it turns out, and this is one of those things that physicists guessed, and we'll see how we guessed it from the Park-Taylor ansatz in a little bit, but that this nine-dimensional form, which is the top form, the top dimensional form on the nine-dimensional space of 3×6 matrices modulo GL3, is actually can be written in a much more suggestive way. It's the 3×6 volume form minus the 9 redundancies. That's what divided by vol GL3 means. It means eliminate the treating it as a gauge redundancy or something. So eliminate the 9 degrees of freedom you'd like here. And then it's just a product of all of the ordered minors of this matrix. That looks a lot like Park-Taylor's denominator. It's very suggestive. And this is actually much more general. It turns out that if you follow the sequence all the way down for general K and N, so this is the top form is labeled by a permutation. It's very simple. N goes, leg A goes to leg A plus K. And then this is what you will find. You'll find that. And the dimension of the form is just equal to how many transpositions you had to take to get down to the identity, to a decoration of the identity. Okay. So actually, this is a proof that all on-shell diagrams in planar n equals 4, at least, take this form. They have some differential form that can be constructed this way. I can give you the permutation, and now you know how to construct this form. You know how to construct this matrix representative. And this is the formula. The number of delta functions is always 2n. So this is 2 times k, and this is 2 times n minus k. You add them up, it's 2n. So it's 2n minus 4 net constraints beyond momentum conservation. It's also easy to see that geometrically that this list of constraints imposes momentum conservation, because it says that c is orthogonal to lambda tilde, and yet lambda being orthogonal to lambda, that c to the orthogonal complement of c is equivalent to saying that c contains lambda. So among these constraints are lambda dot lambda tilde. Okay. Now the space of measure-preserving diffeomorphisms, this is something we showed constructively, is the Yangian. This is exactly what people talked about, what was discovered as an infinite tower of further symmetries. The infinite dimensional symmetries of planar n equals 4 correspond exactly to measure-preserving, volume-preserving diffeomorphisms on this space. But even if there's less supersymmetry, so there's some prefactor, the same statement applies. It's the space of diffeomorphisms that leave this invariant. Why are these symmetries, by the way? The reason is because a diffeomorphism in these coordinates changes this matrix. It changes the dependence on the coordinates in this matrix. And you can always use these delta functions to trade a transformation of the coordinates into an active transformation of the lambdas and lambda tildes. And so this is a real symmetry. It's not a redundancy. It's telling you that you can take this set of lambdas and lambda tildes and take another set of lambda and lambda tildes, and they correspond to exactly the same function, the exact same evaluation. So it's a real symmetry of the theory. And the infinite dimensionality is kind of trivial with functional relations. Okay. So that's one road to the Grassmannian, and it's a very productive one. And you can already see where the combinatorial story goes, is there. And by the way, I hope I didn't have a slide for this, but you should be able to appreciate that the recursion relations can be easily recast as combinatorial maps. So it's very easy to generate the list of permutations that comes out. It's very closed form and recursive. And then using this deconstruction or construction of the functions, you can then get the functions out. You don't need a deep down, the code can be thinking only in terms of permutations. Okay. Now, it's worth studying the geometry of this. We've already seen that the Park-Taylor, in fact, the generalization of Park-Taylor for k by n matrices, has this volume form. Here I'm writing lambda, but you could just equally write c. Just imagine a 2×4 matrix, and then we're looking at this differential form where the minors are, where the volume form is just the product of all of the cyclic minors of the matrix, the n cyclic minors of the matrix. And this is a nice place to start. Physically, we can think about taking our Park-Taylor amplitude, the MHV amplitude, and then moving around in kinematic space and accessing singularities of it. So the first point is that the dimension of this space, the kinematic space, which is a two-plane in 4 dimensions, is 2 times 4 minus 4 dimensional. So this is a 4-dimensional space. And it's hard to draw 4-dimensional spaces, but if the minors are all positive, let's just suppose that they are, we can think of the columns as living as points in P1, and if they're real, we can think of them as points in RP1, and RP1 is a circle. which means that no matter what, as long as we're taking these lambdas to be real objects, they correspond to ordered points on a circle, which is a way of saying that no matter what 4 points you take that are real, any 2 by 4 matrix is positive with respect to some ordered list up to cyclic. So meaning that give me a random 2 by 4 matrix and I can permute the columns and it will be positive with respect to some ordering, because the positivity here just means that they're ordered on the circle. So 1, 2, 3, 4 are ordered points. And now we're going to look at the boundaries. It's obvious why we want them to be ordered here, because the codimension 1 boundaries correspond to 2 points along the circle colliding. For example, say 3 and 4 collide. That corresponds to this on-shell diagram, and it's a 3-dimensional boundary of the 4-dimensional space that looks like that. We'll see how its geometry emerges later. Or you could have points 1 and 2 collide, and that gives you this kind of 3-dimensional prism or pyramid as a boundary. Or you could have points 2 and 3, or 4 and 1. And so we have 4 codimension 1 boundaries that are 3-dimensional. Okay? These things have further iterated boundaries of the following form. They correspond to removing edges from this graph. I didn't put the permutation labels, but it's the same kind of thing. And so what you see is that there's a bunch of 2-dimensional boundaries, and they're arranged in this kind of way. And then you have these other ones. And then at 1-dimensional boundaries, which correspond to matrices like this, where all of the columns of the matrix, well, one column is 0 in this case, these 2 columns are proportional, and this one is distinct, so that's represented as 2 being some distinct point on the circle, and 3 and 1 being identified, and 4 not being there at all. You can kind of map out the full boundary structure of this geometry, and you will land on something that looks like this, which interestingly was written down by Grassmannian geometry in a generalization of the dilogarithm. I'm not telling you the story about how this is related to the dilogarithm, but this is a story which ultimately led to matroid theory historically, and was more or less abandoned because it wasn't appreciated that positivity was at play here. Positivity for 2 by n matrices, again, positivity is artificial because if they're real 2 by n matrices, they're always positive with respect to some ordering. So positivity is always there. Yeah. Okay. Let's come up with, this is actually historically the first road to the Grassmannian, before we understood the combinatorics of these diagrams or anything like that. And it was related, or one way to see it was to think about generalizing Park-Taylor in the following way. So remember, we have this formula for the MHV amplitude. This is Park-Taylor. For those of you who, I haven't really reviewed supersymmetry, so you can just ignore this little eta tilde business. It's just some polynomial in lambdas. We don't care about it except for when we compute particular helicity amplitudes. This thing would be theory-dependent prefactor in non-supersymmetric signals. Or it's a machine for generating components. Doesn't matter. So this is the Park-Taylor amplitude. And we've just learned that we should think about this as actually being something like this positive Grassmannian of 2 planes in n dimensions, and we would like to generalize it in some sort of way with a question mark. What does that mean? Okay. Now, obviously, so we want to upgrade lambda to be some m by, or k by, did I use m or k? M by n matrix C. And obviously, whatever it is, this set of constraints had better include that set of constraints. So one system is that one part of the constraints has to be that whatever lambda gets generalized to, it has to include lambda as a 2-plane inside of it. Otherwise, you're not capturing that momentum conservation. So whatever the C plane is, it had better hold lambda inside of it. And there's a somewhat convoluted way of saying that, which is that that lambda is orthogonal to the orthogonal complement of C. So that tells you that C contains lambda. So it means that in the setup here, we have an M plane C, an M by N matrix that includes lambda among its span, and it has to be orthogonal to lambda tilde, and it has to contain lambda. So you'll notice now that in this kind of form, we have, again, 2 times n delta functions and 2n minus 4 net delta functions. Okay. Let's see, again, is there some sense in which the 6-particle m equals 3 amplitude looks like this. So here we have a 3 by 6 matrix. And what we're going to see is that there's a little subtlety here to begin with, which is just, it's easy to see from just counting degrees of freedom. The number of delta functions we have here available to constrain C is 8. But the space of the Grassmannian of 3 planes in 6 dimensions, which is 3 times 6 minus 9, is 9. So in general, there are 9 internal degrees of freedom inside these C's here. And yet, we only have 8 delta functions. So there's some one parameter left after you've imposed all of these delta functions. There's still a one-dimensional or one parameter family of configuration C that satisfy all of these constraints. And this formula on the right-hand side depends on that undetermined parameter, that one parameter. And it's easy to actually construct that matrix concretely. Namely, we can just eliminate all of these constraints by just putting lambda in the top 2 rows if we want. And now we just have these 3 by 2 constraints, the first 2 of which are exactly lambda dot lambda tilde. And then we have this last one, which is a one final constraint among these things. And when you work it out, there's one undetermined parameter there. So what we can think of is that whatever this undetermined parameter is, and I'm not being very explicit here, it's just called tau, whatever this thing is, it has poles. And you can move around in this space, and there are poles where 1, 2, 3 equals 0, or 2, 3, 4 equals 0, or 3, 4, 5 equals 0. And these poles are special cases of C. They're not generic 3 by 6 matrices. So if you take the residue around 1, 2, 3 equals 0, you get this matrix. And now there's a unique solution to all the constraints, right? You've now eliminated all the redundancy, and now you have a function just of kinematics without any internal degrees of freedom. And it corresponds to a positive configuration where minor 1, 2, 3 is equal to 0. It means they're collinear, or the span of those 3 points is 0, or the triangle built out of those 3 points is collapsed. Okay? But there's other poles. There's a pole where minor 2 equals 0. There's a pole where minor 3, 4, 5 equals 0, or where 4, 5, 6 equals 0, or 5, 6, 1, or 6, 1, 2. So that means that in this tau plane, in this undetermined parameter, this differential form has 6 places where something special happens. And a residue around any one of these poles will correspond to a function of just the kinematics, so some specific function. And we can look at one of these things concretely. In this case, it's kind of easy to see. Remember how I told you that there's a unique 1 plane that's orthogonal to a 3 plane? Well, this set of equations, dotted into lambda tilde, only involves 3 lambda tildes, 4, 5, and 6, and there's a unique orthogonal complement of 4, 5, 6, and it's that. So, which is a long way of saying, this is a matrix which is orthogonal to lambda tilde, includes lambda, and has this minor equal to 0. So it exactly corresponds to this residue. And what is the function? Well, the residue around 1, 2, 3 equals 0 is pretty easy to write down. It's just all of the minors that are, we've delimited this piece. And I actually worked this out so there's no Jacobian in it. It's kind of easy. It's the only way for me to remember this formula, actually. So you look at this 3 by 3 minor, and the lambdas get a little determinant times square bracket 5, 6, and then this is angle bracket 2, 3. So you get 2, 3, 5, 6 from that. And then 3, 4, 5 is this thing in this notation. I'm not sure if Shruti reviewed this kind of notation, but it's that determinant. That can be the definition of it, if you'd like. It's a sum of 2 products of things like this. And then there's this 3 by 3 determinant, which is also just called a Mandelstam, S4, 5, 6. It's the sum of P4 plus P5 plus P6 squared, etc. And then this gives you the formula. Now, what about the component amplitudes? Well, if you know the supersymmetric language here, the way this is encoded, this is a big list of terms which encodes particular component amplitudes for this function. So suppose you were interested in the one that had minus helicity in 2, 4, and 6, so the alternating helicity amplitude. Well, then you would just pick out this term in this expansion, which is just minor 2, 4, 6 to the 4th power. Minor 2, 4, 6 is this expression up here, and this indeed generates the plus minus plus minus plus minus component of that superfunction language. So there's one function here, and we already know that this superfunction, whatever it is plus its rotation by 2 plus its rotation by 4 generates the full answer. And indeed, this is the alternating 6-point component amplitude. So we can generate it kind of conveniently like this. But besides writing down expressions, because clearly if you're following this, there's a lot of stuff going on here. One thing that I want you to take away, even if you didn't follow those details very closely, is that the identity that we had, remember this identity that we had, that there was 3 graphs that were all rotated by 2 in their permutation labels and in the, in the function, could correspond to, one of the BCFW formulas could be 1 residue of 1 plus residue of 3 plus residue of 5 is equal to the amplitude, or minus, it depends on how you're orienting these things, is equal to 2, 4, 6. This is the way we normally put signs on these formulas. So it's 1, 3, 5 is equal to 2, 4, 6. Of course, Cauchy's theorem would tell you it's opposite. Doesn't matter. So, but the point here is that this functional relation, this 6-term identity, that these 3 functions are equal to those 3 functions, the sum of those 3 functions, is now a very obvious instance of Cauchy's theorem. And we now have a picture for what these amplitudes are. And much more, and more generally, what we see here is that no matter what, this, for a general m and a general n, the dimension of the Grassmannian is m times n minus m squared. That's the big space. And the number of delta functions is always 2n minus 4. So that means that you need to take residues until you get down to only 2n minus 4 undetermined parameters, which might take many levels, but that those are residues that correspond to on-shell functions with delta hat and delta hat equal to 0. So those are the normal functions. And it was originally a conjecture, and it's something we're going to prove constructively in just a few minutes, that the residues of this differential form are in one-to-one correspondence. All of the residues, including the top form, are exactly the on-shell functions of planar maximum supersymmetry. So that means that you start with this generic k by n matrix, and you just take a minor equal to 0, consecutive minor equal to 0. Now, I remember when we were first talking about this, Ed Witten asked over lunch once, like, how do you go down, 3 by 6, we have 9 factors we can go down to the bottom, but you only had 6 factors in the denominator. How do you take more than 6 residues? Well, the answer is that these minors are generally mth degree polynomials in the components of the matrix. And when you set minor 1 up to m equal to 0, these things factorize. And so you can actually expose further residues as you go down in this form. Yeah. So, but this just begs the question, and this was an open question. This is how we actually kind of, not exactly independently, but I'd say this is how we posed the question before we understood the answer, which is just how do you label the contours of this thing? How do you label these random residues that you get? How are they classified? And what relations do they satisfy? How are these residues identified with on-shell diagrams? All right, so this is actually relatively easy to construct, but with a lot of hindsight. Okay, so there was a point before we understood anything, and we were meeting with some really brilliant people at the Institute, and over the weekend, one day, Pierre Deline came in and explained to us, oh, there's an easy answer to your problem. And I'm going to explain it to you now. And it's brilliant. You start off with a lot of extra stuff, and it's all going to disappear in just a moment. You look at one example, and it's done. And now you never need to think about it ever again. So his first observation was just that whatever you get by these iterated residues only involves consecutive lists of columns. It never skips over things. So it's only involving like 1 through m, or 1 through m plus 1 maybe, but anyway, always consecutive lists. And setting a minor equal to 0 is just lowering the rank of some list. So he suggested, let's just label all the consecutive rank data in a table. So in particular, and this is way overkill, but let's just look at it this way. So we're gonna use this notation here to denote the rank of the space spanned by columns A up to B. So we're gonna just populate a big data. So 1 up to 1 is the rank of column 1. That means that it's 0 if the column is 0, and it's 1 if the column is not 0. And 1 up to 2 is 0 if they're both 0, et cetera. So you just write down the rank of the span of these columns all the way up, and then you're gonna write it, and the offset, the writing it on an angle will be clear in just a moment here. But we're just gonna tabulate this over complete list of data. And as soon as you start tabulating it like this, you see easy you can actually extend it infinitely in all directions. Because there's cyclicity, so n to n can also go, you can just talk about n plus 1. So there's a periodicity in this table of data. But also, there's no reason why we can't go up forever. 1 to n is also the same rank as the span from 1 to n plus 1, which just adds back column 1. It doesn't increase the rank. So we can go upwards for infinity. And we can even go downwards. So for example, it makes sense to talk about the span from column 1 up to 0, the predecessor of column 1, which is an empty list. Empty lists always have rank 0. So we got a bunch of zeros down here along this diagonal. We have k's forever up here, and this whole thing periodically repeats along this diagonal strip here. Okay, so whatever this data is, it clearly classifies any residue of this differential form that we care about. Now let's see, in the next slide, we're going to see one example and understand why it's A, exactly equal to the diagrammatic permutations that we just saw, and also why you don't need the table. So consider a generic configuration in G48. So these are columns, 4x8 matrix, so we're going to view as 8 points in P3, the configuration, and they're just generically splattered around P3. So no minors are 0, everything is non-zero, and whether it's positive or not actually makes no difference to this discussion. This discussion relies on positivity in no way whatsoever. Okay, so obviously, I can't really stare at a table like this and make any sense of it, so I color it. So let's color it. And obviously, every column has rank 1, every pair of columns has rank 2, every triple of columns has rank 3, and if you have 4 or more columns, you just get rank 4. So it's a very stupid, simple table. Okay. Now consider a residue that we could take. A residue that we could take of this form would have to set a consecutive list of 4 columns to be 0, and we can do that, for example, by throwing column 8 on the plane 6, 7, 8, 1. Just one example, for example. So as it reaches that plane, the only thing that changes is that this entry of the table, which was 4, which is the rank of the space from of the span of 6, 7, 8, 1, suddenly becomes 3. That's it. No big change. Okay? Now we can say bring column 3 up to the plane 1, 2, 3, 4, and we get that thing. We're going to put column 5 on the plane 4, 5, 6, 7. We can keep going. And as you see this, what you can see is that you get iteratively simpler configurations. And what you can see is that every one of these rank tables is completely characterized by the corners that it goes through. And this is actually easy to prove because you know that whatever this rank table is, it monotonically increases going upwards and it monotonically increases going from right to left. So the corners dictate the whole thing. And in fact, if we decorate it this way, it's easy to see that you could write down the whole table from just knowing where these corners are. And these corners, of course, encode a permutation. In the following way, we shift the labels over a little bit. So 1 goes to 6, or 1 goes to 5. 2 goes to 4. As soon as you look at this, you think you understand everything. 1 goes to 5, 2 goes to 4, 3 goes to 8, 4 goes to 7, 6 goes to 10, etc. And it's also kind of naturally decorated, this permutation. There's a distinction between a point going to itself plus n and a point that goes to itself directly, which means that the span is, that it's a vanishing column. Okay, so you've looked at one example. You now understand completely that all of the residues of this Grassmannian differential volume form are labeled by permutations. Let's hope they're the same permutations. And it's easy to characterize how to define this geometrically, which is that if you look at this set of column vectors, you know, k-dimensional columns in n dimension, or there are n k-dimensional columns, k vectors. What you do is you look at the span of all the consecutive lists. So, and for every column A, there's a unique nearest neighbor, B, meaning nearest to the right, so above A, beyond A, in which column A is spanned by that range up to B. Okay? So in particular, if B can be equal to A, in which case this list is empty, and that only happens if the column vector is actually 0. So that's the dressing. And it's only, yeah, so, and this label defines a permutation. So so for example, what we mean by 1 goes to 5 means that the column vector 1 is not spanned by 2. That means it's not sitting on top of 2. It's not proportional to 2. However, and it's also not on the line 2, 3. It's also not on 2, 3, 4. 2, 3, 4 spans this line, and 1 does not lie on it. But it is spanned by 2, 3, 4, and 5, because it lies on the plane 2, 3, 4, 5. So 1 goes to 5. And similarly, 2 is not spanned by 3, but it is spanned by 3 and 4, because it's along those lines. So that's how you encode this permutation label. Okay. Now, interestingly, this permutation, this geometric picture also immediately tells us how to talk about dimensionality, say, of these configurations. Like, what is the space of k by n matrices, modular GLK, that satisfy these consecutivity constraints? And the reason is that you know that for example, 1 being on the plane 2, 3, 4, 5, because it's a plane, it tells you that there are 3 numbers that are required to specify it. Everything is projective here. So it means that you need at least like column 2, 4, and 5, or 2, 3, and 5. There's a 3-dimensional space of things in order to write down the span. That's easy to see because 1, you need 3 dots to write 1 in terms of this, the basis of the 3-dimensional space, 2, 3, 4, 5. So these 3 dots mean that there are 3 degrees of freedom needed to specify column 1 in terms of its neighbors. There are 2 dots, meaning that column 2 can be specified by some multiple of column 3 plus some multiple of column 4, 2. And then 4 dots, 3 dots, 4 dots, etc. So the number of dots is exactly counting the number of degrees of freedom you need to specify this configuration, except the k squared or the m squared, the GLK is not being counted, or is still redundant here. So you just count the number of intersections inside this kind of, it's called a juggling pattern, or we thought of them as Deligne tables, and that tells you the dimensionality offset by k squared. This immediately also tells you how to talk about boundary configurations. So which configurations are accessible from some of them? Namely, there are permutations which are related to these things by deleting one green dot. And in particular, that means they are labeled by permutations which are transpositions of the original permutation. It does not need to be adjacent at all anymore, such that the dimensionality drops by 1. So you just look at this permutation and you transpose all possible pairs, and if the number of green dots drops by 1, that's a boundary element. So for example, what A and B do not need to be adjacent, but if you transpose, and if they intersect like this, it deletes that green dot. And is it okay for, say, another permutation to go somewhere like this? Yes, because it just changes, this green dot moves over. So this started off with 2, it goes down to 1. That's okay. It's also okay for there to be something between A and B that has an image outside of the images of A and B. Those things are okay. The one thing that you're not allowed to do is to have something, this is okay. The one thing you're not allowed to do is to have a column between A and B whose image is between the images of A and B. That's the one thing you're not allowed to do, and it's easy to see that if you had any hook like this, that it would delete more than 1 dot. In fact, it's like codimension 3 in this case, or maybe higher, depending on how many other hooks you have that are configured like that. So this is the combinatorial description of now this purely geometrically, how you can talk about a configuration and the boundary configurations and how they're related to permutations. And this boundary rule is entirely combinatorial. So this is another way of saying it. About any leg A and B can be transposed, or the images of A and B can be transposed, provided that there's nothing from region 1 going to region 2. Then that is a boundary element. And that defines a set of boundaries. But it also allows you to now do the bridge construction that we had. So for example, we can take a boundary exactly like we did before and get a successively simpler configuration, just like we built up the functions. And what do we land on? We land on a 0-dimensional configuration, which just has non-vanishing columns 1, 2, 3, and 6, like this, labeled by this trivial permutation. And we can bridge it back up. In fact, we can use the exact same coordinates to parameterize this configuration that we were interested in. And the sequence of operations is exactly the same, and the equivalence of this story with the previous one tells you that the geometries are labeled by exactly the same permutations as the on-shell diagrams. So remember this BCFW construction. This is not about recursion relations. It's just about decomposing a permutation into transpositions. So I hand you this permutation, and you can write this permutation as a sequence of transpositions on something trivial. As soon as you do that, you have a representative diagram labeled by that permutation. And by doing the geometry thing, you also know that this geometry, with its permutation labeled in the way that I just defined, which has very little to do with the on-shell diagrams. So just intrinsically, this geometry is labeled by exactly the same permutation, and a representative span of that subspace can be generated by exactly the same sequence of transpositions. And this is how we get the function. So now we understand this entire map, that planar n equals 4, the set of on-shell diagrams is encoded by combinatorics, which encodes geometry, which encodes these actual matrices, which encode actual functions. And these actual functions can be also viewed in this once conjectural form of the consecutive minors of the matrix on some contour integral, or some residue really, because I'm not including the pi's, or the 2 pi i's, that is labeled by the same permutation as the function, and this geometry is labeled by the same permutation. So the entire story, and this is going to allow us to use intuition about the geometry. For example, homological identities in the Grassmannian. These configurations plus this configuration plus this configuration, if they connect geometrically, so if they are homological inside the Grassmannian, means that it is a list of on-shell functions which add up to 0. That is very powerful. And allows us to classify things, like to count the number. There's a closed formula for the number of independent on-shell functions for any n and k. It is a empirically discovered formula, so there's no proof of it. But the number of independent superfunctions you need to talk about scattering amplitudes to all loop orders there's a known formula. So it's not interestingly, I do not have a closed formula for the number of superfunctions. I only have a closed formula for the number of independent superfunctions. So only when you delete all the identities, then I surprisingly have some nice pattern that you can recognize in the online integer sequence database. But that's another story. Okay, so this was the point of this lecture. Tomorrow, I will talk about, just before lunch, we're going to actually develop this correspondence in a couple other ways, which I hope will make it more transparent, and we will see how this correspondence, so when we go to non-planar graphs, almost everything in the story survives except for the combinatorics. So we're going to lose the combinatorics. However, the correspondence between this and the geometry is sound, and it's going to allow us to classify the number of non-planar functions in non-planar supersymmetric Yang mills. And if you're interested in problems to work on at home, I mean open problems for research, in an incredibly interesting, but apparently hasn't gotten much attention yet, is the number of inequivalent decorations of these things. So if you just adding orientations is now talking about non-supersymmetric theories, and all it does is change these things by prefactors, which depend on the spectrum of the graph, the oriented graph. And it is not known, or at least I haven't been able to find a combinatorist who knows the answer to how many independent orientations can be assigned to the graph that give different spectra. That's a fun exercise. So we don't yet even know the number of functions you need for pure Yang mills, even in the planar limit. But we do know it's a finite list. You can explore that by empirically generating them if you'd like. Okay, this is a long story. There's a few years ago, my collaborators and I wrote a book. So there's a pretty, you should all buy it. I think I get €1 if you buy it. It's made me 100 air. This is, all the details for this planar story are laid out here. And as soon as you go beyond planarity or maximum supersymmetry, it becomes open problems for research. But this general correspondence is still extremely useful and as a practical foundation. So anyway, thank you very much.
Question?
So what is the Jacobian of the GL for gauge fixing in your previous slide?
Oh, the Jacobian of the gauge fixing. It depends how you set it up. We tend to be very, it turns out this is a story where you can be very sloppy and always get away with it. So if the gauge fixing corresponds to setting a minor to the identity matrix, a k of the columns to the identity matrix, then the Jacobian is 1. So that's what we usually do in practice, is you just pick k of the columns to be the identity by dotting into the inverse of that. Like if I have a generic k by n matrix, I dot into the inverse of the submatrix involving k columns, and now you would just evaluate that expression on that matrix, and the Jacobian is 1.
Okay, any other questions, remarks?
Oh, on the subject of being sloppy and getting the right answer and Jacobians, this is something that we had long discussions with my collaborators about this in the book, because this perp notation is a little ambiguous. Lambda perp, or C perp, the orthogonal complement of C, is only defined up to GL n minus k. It has its own symmetries. So I'm not talking about a unique matrix. I can do any GL n minus k rotation of it. So surely we need to have some clarification about what you mean. And it took me a long time to even appreciate this fact, because in Mathematica, there's a function called null space. If you give it a k by n matrix, you put null space on it, and it gives you an n minus k by n matrix. And it turns out that introduces no Jacobians. So you just solve for null space, C dot something equals 0, and null space of C dot something equals 0. But it's because null space has some clever, or some standardish conventions that guarantee you have a unit Jacobian. And if, more generally, so actually in the book we define that in a more rigorous way that won't ever lead you awry. But as written, it's a little sloppy.
So I don't see any other questions, so let's thank Jake again. And see you at 4:30.